Can you hear me? Perfect. So I'll start. Good morning, everyone. Thanks for inviting me here to share my work with you. I'm Viola Gelli from the University of Florence. And today I would like to discuss with you about the fact that one of the very interesting great things that JWST is starting to do in these first months of observation is revealing the very first Quiescent galaxy at very high redshift, so directly in the Epoch of Reionization. And in this context, I will show, first of all, let me say that when I speak about quiescent galaxies, I mean that these galaxies have no ongoing star formation at the time of the observation. And the very first detection was reported in this paper by Loser and collaborator, and is a galaxy detected within the JWST survey. And this is the very beautiful spectrum of the redshift 7.3 galaxy, and it is a galaxy with a low stellar mass in the low mass regime of 10 to the 8.7. And the interesting thing is that this spectrum shows no ongoing star formation at the time of the observation. Interestingly, just a few weeks later, another paper was published of a similar, let's say, object. This time, this is a lens galaxy published by Strait and collaborators. It is at slightly lower redshift of 5.2, and it has even even lower stellar mass of 7.6. And also, this galaxy is post-starburst, so it experienced a very rapid suppression of the star formation after a burst of star formation. And I believe that the very existence of this type of quiescent non-star forming galaxies at very high redshift trigger some very interesting key questions that we need to address. So how do these low mass systems come to existence at in the high redshift universe? What are their duty cycle and what drives their evolution? And can we use really these JWST detections to learn something about feedback processes happening in high redshift and quenching mechanisms? And the main tool I've been using to try to address this question are cosmological zoom-in simulations, in particular the ones developed by Andrea Pallottini, like this one I show here. And these simulations are developed to target mainly massive, highly star-forming galaxies up to redshift 6. But as I told you, I'm interested in understanding feedback in the lower massive systems. So what I did basically was targeting within all the simulation the galaxies with a stellar mass below 10 to the 9.5 solar. And not only the isolated low mass dwarf galaxy evolving in the cosmological volume, but also those low-mass galaxies that are found as satellites living nearby more massive systems like the one I'm showing you here. Because in this way, I could also really take into account the possibility of also environmental effects having an impact on the evolution and quenching of these low-mass systems. And I performed this kind of search in all the latest set of simulations, the Sarah simulations. And so I ended up with a large sample of about 200 low-mass galaxies in between redshift 6 and 8 that allowed me to, let's say, have a good statistical sample to make comparison with upcoming JWST data. And if we have a closer look at the properties of this low-mass system at high redshift, we find that this can be mainly divided into two big categories. Which I show here in this zoom, in this example of a snapshot of the simulation. And from the one hand, we have actively star-forming low-mass galaxies. There are typically more massive forming stars, and they typically have also a disk-like structure. On the other hand, we also do find in the simulation many quiescent systems. And indeed, these quiescent systems are usually smaller, both in size and in mass. And as you can see from the gas density map there, they do lack of the gas available for star formation, and this is the reason they're not forming stars. And as you can see, we thought it would be challenging to detect this kind of very small and presumably faint systems too. So to understand if their observation would be feasible, what I did in this paper about 2 years ago was create a set of synthetic SEDs and mock images for JWST. And this revealed that, yes, indeed, the typical spectra of Quiescent galaxies were red and basically very faint, but also that in deep near-cam images exceeding about 20 hours of observation, this quiescent low-mass galaxy would have been revealed. And how many did we expect based on our statistical sample? This is the distribution of the star formation rates of the galaxies in between redshift 6 and 8, and you can see that 30% of the low-mass sample is made of quiescent galaxies. And if we check the mass of this system, so this is the fraction of quiescent galaxies per stellar mass bin, we clearly notice a decreasing trend, meaning that really these low-mass quiescent galaxies are dominant below 10 to the 8.3, so a very significant part of the galaxy population. But what is the physical mechanism that drive this quiescent? And to understand this, we really need to go deeper into the star formation histories of these systems. Here I show some example of star formation rates over cosmic time of different simulations arriving to different redshift, which can be seen as the observation redshift. And what we notice right away is that all the systems in the simulation at high redshift have a very bursty and feedback-regulated evolution. And we also notice that particularly the low-mass ones are also characterized, all of them, by many periods of quiescence during the revolution. And here, with the field color, I highlighted the evolution of those galaxies that are found to be quiescent by the end of the simulation. And what we can notice is that all of their evolution are characterized by a very smooth and gradual decrease of the star formation. And this is really typical of supernova feedback. So it is really supernovae which are intrinsically characterized by a delay in the explosion of stars of different mass that causes this type of gradual smooth decrease of star formation leading to a quenching. Among these galaxies, I gave a name to this one, which is Lilium. And the reason is that this simulated galaxy shows very remarkably similar physical properties as the observed one by JWST. So it has the same redshift stellar mass, and it has also been quenched by the same amount of time, which is about 20 million of years. And another quantity that is important to quantify to characterize the evolution of this bursty system is their duty cycles, which I defined in this way. So it is the amount of time during which the galaxies are forming stars with respect to their total age, basically from their formation. And this is the distribution of the duty cycle with respect to the mass. And you can see that there is a clear increasing mean trend, meaning that galaxies with mass above about 10 to the 9 have been forming stars for most of their lifetime, more than 90% of their lifetime, while the lower massive systems can have a wide range. And here in the middle there you can find the Lilium, which once again has a duty cycle which is similar and consistent to the one derived with SED fitting codes, which are the black error bars there, for the observed JWST galaxy. So we have that this simulated galaxy is remarkably similar to the observed one. Let us now proceed to compare the synthetic SED to the observed one. And what we get is this. The green curve is the synthetic SED, and the black dots are the photometric points with the near cam. And we clearly have some kind of a problem here because we have about 0.5 dex difference. So what could have caused this high discrepancy? The first explanation I tried to investigate was regarding the stellar metallicity. Because one thing that I didn't mention before is that the metallicity of the two galaxies are actually different. Because our galaxy, Lilium, shows a very rapid enrichment in heavy elements due to the supernova explosions and reaches solar, while the metallicity observed for JWST is about 2 orders of magnitude lower. So this may be the reason. But to test this, I artificially changed the metallicity of our simulated galaxy to the observed value of -2. And this other curve is the result. And as you can see, yes, the flux is now higher, but still not enough to reach the observed value. So this is not the explanation we are looking for. And to really find the cause of the discrepancy, we have to once again analyze a bit more into depth the star formation history of the galaxy. Here you show this, I show the star formation rate versus look-back time for Lilium, which, as you can see, start forming starts about 120 million of years before the observation. But also we noticed that the bulk of the stellar mass, or more than 80% of the stellar mass actually, is formed about 90 million of years before the observation. From that burst, then the star formation rate is gradually suppressed due to supernovae until it's reached 0. Let us now compare this star formation history with the one that is directly derived from the observation with SED fitting codes, which is this one, which is, as you can see, very different, basically a top hat, and the main difference is in the stellar ages, because the stellar ages of these top hat star formation histories are much younger, about 30 million of years. And in order to have such star formation history, we have to, the galaxy have to pass from a very high star formation rate to 0 in very rapidly. So it is this need for a very abrupt quenching of the galaxy after a burst of star formation, the explanation that could lead us to understand this kind of emission. And to test this need for a very abrupt quenching in galaxy, I artificially imposed an abrupt quenching in our simulation. So I imposed that right after the main star forming peak, in which most of the stellar mass of the galaxy is formed, the star formation rate is completely suppressed. And then I shifted to match the observational redshift. The orange spectrum here is the result, which now agrees with the data. So we really need this abrupt quenching to reproduce the data. But as I told you, supernovae are intrinsically characterized, as we saw in our simulation, by a gradual decrease and a smooth decrease of the star formation rate, and cannot produce this abrupt quenching. So really, supernova feedback cannot be the responsible for the quenching of this observed 7.3 galaxy. We do really need additional physical mechanism on top of that. So now it's, I think, the time to really investigate possibilities. And I can suggest some solution that is now important to investigate. One could try to explain this quenching with environmental effect, but actually I don't think that is the case, because typically environmental quenching happens on longer time scale, more than 100 million of years. So we do really need faster processes that could be like AGM feedback that is very rapid, or also some radiation pressure that will be a natural outcome that will be expected after a burst of star formation. And this could drive really a powerful outflow that could lead to the quenching of the star formation. And yes, I have arrived to my conclusion. So we have seen that mainly these high-redshift galaxies are have very feedback and regulated and burst star formation histories. And we have demonstrated that supernovae cannot be the responsible for quenching the observed JWST galaxy, because supernovae cannot produce such an abrupt quenching. But also I want to end on an optimistic note with the fact that with cosmological simulation we had been predicting for some years now the existence of these low-mass quiescent galaxies that we are now indeed starting to observe. But from that distribution, you can see that the JWST observation is just at the tip of the iceberg of the quiescent galaxy that we do expect. So really, with future observation, we can go deeper and really use JWST to learn about high redshift feedback. Thanks.
Questions? Thank you for the nice talk. I was wondering, you didn't really discuss this metallicity difference. You know, this galaxy has very low metallicities, yet it has basically turned all the gas into stars. But the metallicity is low, so that means there must have been an enormous outflow in an early phase, maybe through AGN or whatever. So I was just wondering whether this is connected to your problem to some extent, that whatever physics you don't have in the simulation that leads to this difference by a factor of 100 in metallicity also might solve the other problem.
Yes, let's say there are 2 points. From the metallicity treatment in the simulation, we do see that 2 things. Basically, the gas and the stellar metallicity are usually not similar, because we do see indeed these outflows and then gas is accreted, so many times the gas is found to be at lower metallicity with respect to the stars in simulations. And here I'm talking, the one I was mentioning was really the stellar metallicity. And the metallicity of the stars in the simulations is really found to be always very enriched, especially in these low-mass quiescent systems, because they do not get to reaccrete much gas. So as soon as they experience a starburst that enrich rapidly up to solar, then after that the star formation stops, and until maybe later on they will accrete gas again and experience outflow, but that's what we see in simulations. And the observation, yes, we do have that the stellar metallicity is 2 order of magnitude lower, so the possibility is that they have different kind of enrichment, a lower enrichment, or that probably after the starburst also, if in the past they have experienced many starbursts, they blow out the gas, the enriched gas, and accreted more metal-poor gas. But it's really hard, I think, to trace back to the older stellar population. What we can really infer from observation are really the recent stellar population, recent star formation history. And from that, still, let's say the positive note is that even by changing the stellar metallicity of 2 order of magnitude, we do not see that much of a change. So it would really be interesting to understand more about the trend of metallicity and the metallicity of this galaxy, but regarding the quenching and this abrupt quenching, it really does not make much of a difference.
So we can have a quick question.
Could you comment on whether these galaxies are such low masses are satellites or centrals, or do you have some constraints on that? Because that could make a difference in the different proportions.
Yes, you mean in my sample of galaxies that I've been talking about, there are both central galaxy, isolated, let's say, galaxy, and satellites. And if I can show you another plot, the interesting thing is that we do see that all of these galaxies are, their evolution are driven by the inner star formation and the supernovae explosion. And so being this inner physical mechanism that drives their quenching, it really doesn't matter if they are in dense environment or not. And I actually verified this by reconstructing their orbits around the main galaxy. These are satellites. And these are their orbits around the central, highly massive systems, and those are their star formation histories. And as you can see, they are all similar also to the Lilium one that I showed before. And they are all similar because they are all driven by the inner quenching by supernovae. And those red segments, if you can see, are the periapsis positions, so the sign by which they pass through closer to the central system, so when it's more likely for them to be affected by it. But we do not see any connection between those time of periapsis and the quenching. So it really, in the simulation, really this seems to not affect the evolution of these galaxies. But yes, some of them we do see that also develop streams, so I think they can have some effect in morphology, but we do not see a drastic effect on the quenching.
Okay, let's thank our speaker again.